Okay, welcome back, guys. So maybe you notice, so we've not saved our work so far, so please try your best to always get your work saved in case of anything like crash. No, it's not like the the open source tools will crash, but just in case. So to do that, since it's the first time we're saving, Control C, so Control S, and it's depending on how you've set it up, it will take you to the directory where you would like to save. So for mine, so it's in my home directory, so I have a folder where I would like to save it. So that's the design folders, and that's where I want to save it. And what's the name I want to give? So let's say EEE351 lab 1 dot sch. That's schematic capture. That, I think the extension tells it a schematic capture. Okay, I think, yeah, so okay, it's saved now. So we're done. Yeah, as far as schematic capture is concerned, I think this, yeah, we've done all of that. But now we need to carry out simulations, right? So in Spice, so simulation programming for simulation programming with integrated circuit emphasis. You know, like it says, simulation programming. So maybe if you want, you can see Spice as a language. Yes, a language for IC design. Though there is Verilog, let's not confuse them. There's Verilog for digital IC designs, I know, but yeah, that way you can maybe see it as a language too, because if I was not doing this schematic captures here, like picking components, dropping them, wiring them, I could as well write a program for this using the Spice. Yeah, so usually that's, you know, that thing that looks like a program for this whole thing, it's usually called the Spice netlist. So you see, don't worry, we're going to generate a Spice netlist for this, then you get to see what I'm talking about, that it looks like like I'm writing a program, you get. So it's that, you know, it's that code that will now be used by the simulator, by the Spice simulator, to know, you know, at the end of the day, anything you want to do with computer, even if it's just a drag and drop, at the end of the day, it's a simulator that will run it, and computer works with instruction. That's the best way. That's how computer was made to, you know, to operate with instruction. So even the graphics you're making, at the end of the day, it will turn to code one way or the other. So for this, the code for this, it's usually called Spice netlist. For this scheme, there is no GUI for entering. You know, when you want to do your Spice simulation, you need to give Spice directives. So that's Spice instruction. So Spice command, oh, do this, and it's in form of code. You want, for instance, you want to run one of the directives you have, Spice directive you have, it's the transient analysis, for instance, you may want to do. If you want to give the directive, you will say dot tran. If you want to do DC analysis, say dot DC. If it's AC, dot AC. So you can say that's a command. So for you to be able to give the directive here, you need to write somewhat a little code like text here, because there's no GUI for such this thing here, to the best of my knowledge. So to be able to do that, so you just come here again. It's an object. Everything in a scheme is object, you know. So where do you go to pick objects? You go to, you know, components, and since it's just a simulation thing, right, it's not part of what I'm going to be fabricating, I'll just go to the scheme library. So I hope it's getting clear what each of these libraries are for, the scheme and the PDK libraries. So Yeah, so it's not meant to be fabricated. I just go to the scheme. Then what am I looking for? I'll just search for code. So code, then you have code dot symbol, then code shown. They are the same thing. They're going to do the same thing. That's where I want to write my code, my directive for the analysis I want to carry out. You can pick this, you can pick this. But I want to pick this because like it says code shown, it shows me my code, so at any time I can always view it. Okay, let me just add the two and so you see the difference. That's for this. So this blah 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 means that's where you write your directive. And let me do for the other one, insert then code. So you can see this one, there is no blah blah blah, that is, it does not show you, it just shows dash dash dash. It does not show readily like this what you want to. So if I go write something now, let me type, you double click, then I keep on writing like that, so there is a space, and I think everything too would need to be put into quotation, so it continues. So if I'm going to be writing those directives, I'll be seeing them. So that way I would easily know, maybe if I'm running the simulation and it's telling me error somewhere, I would easily know that, oh, something is wrong. Okay, let me just at a glance I'll just see what I'm. But the problem with code shown is that it takes up the space. Yeah, so at the end of the day it's just based on what you need or want. So let me just go with this for now. Let me go with the blah blah blah. So but before we do that, so briefly let's just come back to we're not all done with this, but let it just be here for now. There's one more thing for us to do. We're designing, right? We're designing a CMOS inverter, but like I said, it's not like we have any handwritten specification we're following, but I'm going to do this in such a way that it still follows correct what if you analyze would be turn out to be correct specification at the end of the day. So and when it comes to CMOS design, basically as a designer, basically all what you're doing, you're trying to size the transistors. Yeah, by sizing the transistor, you can, anything you desire the transistor to do, it will get it done, as far as you have the mathematical workings for it. So if you want the MOSFET to conduct this value of current, then all you just need to do is to go to the current equation and specify the sizing that you want. Then then you have the current that you want. Yes, if you check the current equation, yes, it's not, that's the W over 2L mu Cox VGS minus VT all squared. If you check that equation, yeah, it's not only W over L, the sizings that you have there. You have, at least you have the threshold, the VT, the VGS, the VT, you have the VGS also, you have the transconductance parameter, that's the mu Cox. Together they are the product of mu, and that's the mobility, and the capacitance, auxiliary capacitance, is known as the transconductance parameter. So but why did I just emphasize on just the sizing? That's the W over L ratio. Yes, not only the W over L ratio that you as a designer you have at your disposal, you also have the VGS, the gate voltage, at your disposal to control. So actually you have just two things to control. You see the remaining parameters there, the transconductance parameter, the threshold voltage, and what else again there. It's not at your own control. Those things are what will be defined by the foundry you want to fabricate with. So for instance, skywater, right? all those ones, you have to use what skywater gives you, so that one is not at your control at all. In fact, you may not even be entering the values because everything will be at the back end of the spice simulator, so you don't need to worry about that. So what am I trying to say? Let's leave the VGS alone for now. We're not concerned about VGS. Then what we have left is the size into W/L. So we need to size these two transistors here. So how do we size them? So you have to do them in a way that you would follow your specifications, right? So let's quickly check something in OE and Sodini. There's what is called switching voltage, which in your class you may have learned about the switching voltage. Where is it? So this is it here. So that's the VM. There's a formula for it. This parameter is very important, and you can see it's affected by some other things like your threshold, the VDD, the KP and the KN. That's the transconductance parameter. You can see them here. That's the mu. But actually, for OE and Sodini, the mu Cox, which is known as transconductance parameter, is being multiplied with the sizing, but it still carries the unit of the transconductance parameter because W and L are of the same dimension, so they'll just cancel, so you just have only this back again. So what am I trying to say? You see this parameter, this VM, it's very, very important. I will tell you the importance later, but this, you can see it's been affected by all these electrical parameters here and there. So okay, let me first talk about the importance of this VM. So when you're designing, say, a logic gate, you want to talk about the noise margin. You say one of the advantage of digital compared to analog is its noise immunity, but then it's not all the magic. You need to also design such that you have digital abstractions, so you talk about the noise margin and all. So the switching point voltage determines how much noise margin you can have, so that there will not be error between what is low and what is seen as low and what is seen as high. You get so you can see that the VM really it determines what is fundamental about the old digital CMOS inverter. We know about the on and off, the ones and zeros. It's really it determines a lot about it, how well the digital device will give you the one when it's supposed to give a one, and how it's going to give the zero when it's supposed to give the zero. So you can see that the VM determines that, right, through the noise margin, and indirectly it's been affected by this electrical parameter. So again, maybe another reason to appreciate the whole theory you guys have done so far in the course, another reason to appreciate it. So that's why we needed to know about all these things, the mobility, the capacitances and all of that. So yeah, so let me just check the time. Still have time. Let's cut it here. See you guys in the next video. Continue.